Okay, now we're going to hit my favorite topic, maybe my favorite topic in all of calculus, if not all in mathematics. And before we get into it, let's discuss this idea, which is going to be central not only to this last section of topic in integration that we're going to do. It's called improper integrals, but also to the whole next topic, which are called sequences and series. Okay, all of this has to do with how quickly things grow. That's really the key behind the whole thing. How fast do things grow? So these are things that we're going to be proving as we go, but I want to give you kind of a bird's eye view of the whole thing right now, just so you can kind of be aware of it as we go through it. So let's start. I could start with this with either an x or an n. I'm going to put an n there, and you'll see why in a minute. And we're going to just basically consider that our kind of our middle ground and say, what are things that grow faster than n as n grows? Well, obviously something like 5n grows faster than n, because as n goes 1, 2, 3, this one's going to be 5, 10, 15, 20. It's going to go faster. So that grows faster. Then we can get much faster than that by going n squared grows faster than 5n as n gets big. This is going to kind of leave this in the dust. And of course, as soon as you say n squared, you can make it n cubed or n to the 10th or n to the 100th or anything like that. So those are all things that are going to grow faster than the previous one. Okay. So then what's something that grows faster than n to some high power like that? And again, this is all things we're going to be discussing as we go, but something of the form 2 to the n is going to grow much faster. This just leaves this again in the dust. Anything of exponential like this or geometric like this is going to leave something of this form, n to the 10th, behind eventually. This one might as n is equal to 1, 2, 3, 4, 5, this one's going to be ahead. But you go out maybe past 50 or something like that, this is going to be on top, and it's going to stay on top forever. So as soon as you say 2 to the n, of course, then you can go 10 to the n or any other number to the n and things like that. And you can go crazy with this, but one that's bigger than this is going to be n to the n. N to the n grows faster than 10 to the n because, again, as n gets large, this is staying fixed, whereas this gets large right along with this. Okay? And there's one other one that kind of fits in between these two, which grows faster than this, but not as fast as this. And it's going to become especially important as we talk about sequences and series. It's n factorial. Okay, n factorial. Are you familiar with that? And like 5 factorial means 5 times 4 times 3 times 2 times 1. And so, again, if you think about it, you realize why this is going to grow bigger than this. Because if you have 10 to the 10th versus 10 factorial, if n is equal to 10, then this is 10 times 10 times 10 times 10, 10 of those. Whereas this is 10 times 9 times 8 times 7. Okay, this one's bigger. But as soon as you get to, say, 100, and you go 10 to the 100th power versus 100 factorial, well, now look what happens. This is 10 times 10 times 10. You're going to have 100 of those. Whereas here, you're starting at something much bigger than 10. You're starting at 100 times 99 times 98 times 97, and so on, all the way down to 1. So most of these are all going to be bigger than their counterparts there. There's 100 factors in each one, but all these, most all of them, except for the last 10, are going to be larger than these. So this grows faster than this, and clearly n to the n grows faster than n factorial, because like 20 to the 20 power grows faster than 20 factorial. Agreed? This is 20 times 19 times 18, so on. You have 20 factors there, whereas this is 20 times 20 times 20. They're all 20. So this is going to be bigger than that. So anyway, so that's good to have that bird's eye view of just which ones of these grow faster than the others. Then we can also grow slower than n. We could obviously have n over 2, right? That's going to grow slower than n. If you want to get something that grows even slower than that, you could have the square root of n. The square root of n grows slower than that. As soon as you have the square root of n, then you can have, say, the 5th root or the 10th root of n, something like that. That's going to grow slower than this. And finally, something that grows slower than any of these, which is kind of the counterpart to these exponentials up here, is to have the ln of n. Any log would do, but I'll just make it ln of n. We could have stuck e to the n right in here if we'd wanted to. That would grow faster than 2 to the n and not as fast as 10 to the n. But its counterpart is that this grows very, very slowly. Okay, if you think about what the graphs look like, e to the x looks really big, or grows very fast, I should say. So the ln of x, which is the inverse, grows very, very slowly. Okay, so that grows very fast. The ln of x grows very, very slowly. So they're kind of counterparts. So keep that in mind. That's important as we continue on. I'll be referring back to that and saying, yep, isn't that what we said way back then? Okay, so I guess we can keep those up there. Here's the intriguing question we now have. When we defined the integral, the definite integral, we said that the function was something like f of x dx from a to b, and the functions that we looked at were functions that were bounded. F is bounded on this interval. So basically the whole thing could be put in a box. The interval on which it was defined goes from a to b, and the function never gets bigger than a certain thing and it never gets less than a certain thing. So the whole function fits into a box like that, and then you can, whatever you want, find the value of the integral. Okay, but those were the kinds of functions that the fundamental theorem of calculus dealt with. Okay, functions that were continuous on a closed interval. If they're continuous on a closed interval, then if you remember from Calc 1, it means they have a maximum value and a minimum value, so you can essentially put them in a box. Now we're going to think outside the box. Okay, now we're going to extend this idea. So let's take an example. Let's say that we're interested in, say, 1 over the square root of x dx as on the interval from 1 to infinity. 1 to infinity, and we use a little sideways 8 to indicate infinity. We say the word infinity, but what it really means is it means that the real numbers are going to go out farther and farther, get larger and larger without bound. It's not that they hit anything called infinity, but it means that there's no way to cap it. That they're going to continue on. You give me any large number and it's going to push past it. If it does that, then we say it goes to infinity. So anyway, let's get a sense of what this thing might be. First of all, notice that it's not a legitimate integral, because this is not a bounded interval here. So this is called an improper. I guess I didn't leave room to put it, but it's called an improper integral. I don't really care for that name now that I think about it. Okay, I don't know who came up with that, but it sounds like there's something it should be embarrassed of. But it's one of the most exciting kinds, actually, and they're very useful in the real world too. They're used all over the place. So anyway, let's get a sense of what this thing looks like. So here's the graph of 1 over the square root of x. It's a graph that looks like that. There you are right there. It's going to get smaller and smaller and smaller as you go. If you're out here at 9, This is going to be at 1/3. If you're out here at 100, it's going to be at 1/10, so on. It's going to keep getting smaller and smaller. And we want the area underneath that thing from 1 all the way to infinity. We never want to stop, okay? So how do we calculate it? Well, this is a really nice example of what you do in mathematics where you take a couple things that do make sense and you tie them together to get something else that makes sense. Let me make sense of that. So here's what I mean. We know what 1 to b would look like, for example. That's well defined. This is a definite integral, the integral from 1 to b. There's no problem with that. There's also no problem with taking limits of things. This right here is going to be some sort of a expression involving b, so that's an expression, and so it makes total mathematical legitimate sense to say I want to take the limit of that as b goes to infinity. And so there's two things that both make sense, and so we tie them together to say that those two things, when we tie them together like that, that's what we mean by this. That's what we mean by this. Okay? You go from 1 to b, and so that's legit, and then once you have that, then you take the limit of that as b goes to infinity. Let's go ahead and do it, see what we get. Okay, so I guess we can do that easily enough. It's going to be the limit as b goes to infinity. Let me just do a little side work here. This is going to be x to the minus 1/2 power, right? If I bring that up on top, it's x to the minus 1/2 power. So if I integrate it, if I find the antiderivative, I'm going to add 1 to that, which is going to make it x to the 1/2 power divided by 1/2. So divide it by 1/2 is the same as multiplying it by 2. And x to the 1/2 power is just the square root of x. So I guess it's just as simple as that. The antiderivative of this is just going to be this right there. And so there's the antiderivative. Now I evaluate that from 1 to b. And let's see once we get what we get. It's going to be the limit as b goes to infinity. I stick a b in here. It's going to be 2 times the square root of b minus 2 times the square root of 1, which is 2. And now you ask, what happens to this thing as b goes to infinity? Well, as b goes to infinity, what's the square root function look like? It just keeps getting bigger and bigger and bigger. It's going to go off to infinity. So there's our answer. It goes off to infinity. So it turns out, if we wanted to give any answer to what's the area underneath this going to go to as you go out farther and farther and farther, the answer would be infinite. The area becomes infinite as you keep going out farther and farther and farther. Okay? Well, you might look at that and you say, well, that's not too surprising. After all, this function goes on forever, and it's always positive. It never comes down and hits the x-axis. If it ever hit the x-axis, we'd say it's 0 after that, but it's going to keep growing forever. So it might seem that infinity was kind of the natural choice, and you might wonder what all the surprise and all my interest is. But just for sake of space now, let's now change it to this function, 1 over x squared. Okay, 1 over x squared. Now that function is going to have the same general shape. It's going to go through the point 1, 1, the same as this one did. But now, when you're at 9, instead of being at 1/3, it's going to be at 181, right? It's going to be, when you're at 100 here, instead of being 1/10, it's going to be at 1/10,000th. So this graph, if you can see this red here, kind of hard to draw it. It's going to look something like that. Okay? It's going to be You go ahead and plug in the numbers there, and here it's going to be higher, here it's going to be lower than the square root function. Okay? Well, let's do the same thing we did before. Okay? So I'm just going to change all these now to x squared. And so this becomes x squared. Okay? Now, let's do our little workout here. That's x to the negative 2 power. The antiderivative is going to be what? You add 1, and then you divide by it, which is going to be a negative 1 over x. Agreed? The antiderivative of this, you add 1 and divide by it, and then you can write this as negative 1 over x. So here's my antiderivative right here. It's going to be negative 1 over x from 1 to b. Everything else is the same. We're going to take the limit from here to here. We're going to take the limit from here to here. Now let's see what happens. Now what happens? If you stick in b, you're going to get negative 1 over b. And now you're going to get subtract. And now subtract the negative, so it's going to be plus 1 over 1. Stick in a 1 for x here, and you're going to get 1. And now you ask the question, what happens to this quantity? Notice that this quantity here tells you how much area is underneath this function from 1 to b. I could have done this with the previous one too. I forgot to do it. But let's say it's from 1 to 10. If it's from 1 to 10, or let's go to 9 since I have a 9 right. Well, let's make this a 10. Okay, so there's 10. Okay, so 1 to 10, how much area is there from here to here? Well, if we calculate it, it's going to be 1 minus 1/10 is going to be 9/10. What if I go all the way out to 100? How much area is there underneath this red line? If you go all the way out to 100, it's going to be 1 minus 1/100th is going to be 99/100ths. What if I go out to 1,000,000? If I go out to 1,000,000, how much area is going to be underneath there? It's going to be 1 minus 1/1,000,000th is going to be whatever, 999,999 over 1,000,000. It's going to be very, very close to 1, but not quite there. So notice something that's happening here. This limit here, it continues to increase as it would have to, right? As you go out farther and farther, the area underneath this thing continues to increase. Okay, we're accumulating more and more area as we go, so sure enough it shows that. But unlike the other problem where it went off to infinity, here the total area underneath this graph will never get bigger than 1. It'll never get bigger than 1, and in fact, as b goes to infinity, this limit is equal to 1. Okay, so there is I think a rather fascinating problem, and it might be kind of counterintuitive to you. This function here, it never hits 0. It keeps decreasing, but the area underneath it, as you accumulate the area is going to keep increasing. But how big does that area get? It never gets bigger than 1. It just gets closer and closer and closer to 1 as you go up farther and farther. So we would say that the area underneath 1 over x squared, as on the interval from 1 to infinity, we would say that the value of that integral is 1. Okay? So let me explain what we just did here. We just showed that you can have two graphs that look pretty much the same, but the area underneath the first one was infinite, whereas the area underneath the second one was finite. Okay, let me this one here is that, this one here is infinite. Why does one converge? We use the word it converges to 1 because we're talking about limits, so it makes sense to talk about things converging. This converges to 1, whereas this thing, you could say it diverges to infinity, or it just goes off to infinity. What's the reason? Why the difference in behavior? It all depends on how fast these things are growing. See that? One of them, in this case, that one is there, this one is here. This one grows faster, and so 1 over x squared is going to get small much faster than this. This is the denominator is getting big faster. so the fraction is getting small faster. And so that makes all the difference in the world as to whether this thing converges to a finite number or goes off to infinity. Okay, I'm going to say that one more time. That's such a key difference. They have the same general shape, same general behavior. One of them converges to a finite number. The other one, the area goes off to infinity. Why is that? It all depends on how fast these things are getting big. This is getting big fast, so 1 over it is getting small fast. It's getting small so fast that the area underneath it only stays a finite number. Not the case with this one. Okay, so there's all sorts of interesting problems we could do at this point. I want to do some of my favorites here. First of all, one question that you might have in mind is, where's the cutoff point? So let's I guess I have no choice now again but to erase some of this stuff. And let's make a big old divide here. Let's say that these are the ones that converge to a finite number. These are the ones that diverge to infinity. Okay, and so over here we have 1 over x squared dx from 1 to infinity. Here we have 1 over square root of x dx from 1 to infinity. Okay, so what's something which lies between these two? Do you see the obvious choice? What about 1 over x? What happens with 1 over x? What about that? Well, let's do it. This is equal to the limit as b goes to infinity of the integral from 1 to b of 1 over x dx, which is equal to the limit as b goes to infinity of, what's the antiderivative? It's the ln of x from 1 to b, which is the limit as b goes to infinity of the ln of b minus the ln of 1. Well, the ln of 1 is just 0, so all we're interested in is what happens to the ln of b as b goes to infinity. And if you remember from when we learned about the logarithm, the natural logarithm, this goes off, it grows very, very slowly, but it goes to infinity. Okay, it does go to infinity. So, a couple things here. Lots of important stuff. I'm going to make sure my computer is still recording me here. Yep, okay. First thing is we want to put it in here. 1 over x dx from 1 to infinity, that's one that diverges. Okay? Second thing, though, is I want to verify this. I don't want you to rely on just the fact that I told you that ln goes off to infinity. How can I prove it? How can we prove it? Let me show you how we can prove it. Okay, so again, I'm going to have to erase this. I guess I could have done it over here, but I've erased it now, so that's fine. Let's take this function 1 over x right there. Okay? This is the function 1 over x. Let's do this. Let's make a whole bunch of rectangles which lie underneath that function. Okay? So here they all are. You see them? What's the area of each rectangle? Well, let's see. This one, the height of it is going to be 1/2, and the base is 1, so the area is going to be 1/2. Here the height is 1/3, the base is 1 again, so it's going to be 1/3 times 1 is 1/3. This one's going to be 1/4, 1/5, 1/6, 1/7, 1/8, and so on. You agree? So it's clear that the value of this integral from 1 to infinity is going to be greater. It's going to be greater than the sum of all these numbers, right? Because the value of this integral is the area underneath this curve right there. And these numbers are these rectangles underneath it. And so the value of this rectangle is going to be, I'll say greater than or equal to, just to be super safe, but it's clear it's going to be greater than 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9 plus 1/16 plus 1/17 plus 1/32 plus keep on going forever. Agreed? Why did I write it like that? Well, watch. Watch this. There's a 1/2 right there. Here's 1/3 plus 1/4. Notice that 1/4 plus 1/4 is 1/2. So a third plus a fourth is going to be bigger than a half. So this sum right here is bigger than 1/2. Okay? Now you grab the next 4 of them. If you had an eighth plus an eighth plus an eighth plus an eighth, you'd have 4/8, which is equal to a half. But these are bigger than an eighth, so this sum right here is bigger than 1/2. Now you take the next 8 of them. They stop at 1/16. If you had 8/16, that would be a half, but these are bigger than 1/16, so this is bigger than 1/2. Similar, that next chunk is bigger than 1/2. You keep taking the next biggest, each chunk is twice the number of things as before, but every single chunk, and you can do this as many times as you want, is going to be greater than 1/2. So the point is, if I take numbers like this and keep adding them together, that sum is going to get as big as I want it to get. Will it ever get bigger than 1 billion? Sure. All I have to do is take 2 billion of these chunks, and each chunk is greater than a half. So if I take 2 billion of these chunks, the total sum of all those numbers is going to be greater than 1 billion. So it's going to get as big as you want. It's going to go off to infinity. So this is actually called a series of numbers right here, and we're going to get into that in our next big topic. But for now, I'm just using that to show us that the value of this integral right here has got to go to infinity, because it's bigger than all these things, and these things here, when you add them up, they go off to infinity. Okay? So there you go. How are we doing here? Okay, we're at 28 minutes. I guess we'll just do this. I'm going to leave some of this to you. A little bit of algebra here, but you can show that if I take 1 over x to the p, that's going to converge as long as p is greater than 1. For example, 2 is greater than 1, right? If you take anything, you go ahead and do it. Take 1 over x to the 1.0001 and, go through the algebra and go find the antiderivative. You will see that thing converges, okay? On the other hand, over here, if you take anything of the form 1 over x to the p, where p is between 1 and 0, which means that it's something like the square root or the cube root or something like that, or even 1 itself, here see that, we're going to include 1 itself, then those things diverge, okay? So if p is greater than 1, it converges. If p is less than 1, it converges. It all depends on how fast this thing goes. 1 is the cutoff point. 1 is the cutoff. If you're at 1, it diverges. As soon as you jump anything bigger than 1, then it converges. You check that on your own. So then the next thing that I love to do when I teach this, I say, okay, can we find something that falls between these two? Okay, so when P is 1, we've got this one. That one diverges. As soon as you go to 1.00001, now it converges. Can you find something that lies between them? How about this? How about x times the ln of x? I'll make it go from 2 to infinity just so I don't worry about the ln of 1 being 0. Don't worry about that. Okay, why did I choose that? Why did I choose that? It's because the ln of x, see this? It grows slower than any power of x. So right here, if I have 1 over x to the 1.001 power, what that really means is it's 1 over x times the what? This is the 1000th root of x. See that? It's x times the 1000th root of x. And this thing, this denominator, grows so fast that this thing is going to converge. Okay? So I want something that grows. I want something more than just a 1 there, because if you just have a 1, then it diverges. So I want to umph it up a little bit, add something to the 1, or multiply something times the x, but I don't want it to grow this fast. That was too fast. I want something that grows slower. So this is the interesting one. Is that thing going to converge or diverge there? Fascinating question. Is that going to converge or diverge? Well, let's check it out. We can let u be equal to the ln of x, and du is going to be 1 over x dx. And so now this becomes, tell you what, let's first, what's the easiest way to do it? Let's first find the antiderivative. The antiderivative is just going to be 1 over u, and then 1 over x dx is going to be du. So that's the ln of u, and ln of u is equal to the ln of ln of x. See that? So if I want this thing right here from 2 to infinity, I really just want the limit as b goes to infinity of the ln of of b minus the ln of 2, which is just going to be a constant. So look at here. Look at here. As b goes to infinity, this thing here is going to go to infinity, and as this goes to infinity, the ln of that's going to go to infinity. So this thing right there is going to diverge. See that? It's going to diverge. So again, this is fascinating because this is so much fun to think about. This right here, if you take the ln of b as b goes to infinity, that's going to go off to infinity. It's going to diverge to infinity, but it does it super slowly. If you let me try to explain it this way. If you shine light and let that light travel at the speed of light, it'll go around the Earth 7 times in 1 second. That's how fast light goes. It goes around the Earth 7 times in 1 second, okay? So, how big is the universe? The universe is somewhere around 15 billion light years across. That means that it takes light 15 billion years to get from one side of the universe to another. Now already, you can't even conceive what 15 billion years is, let alone how far light's gone in that way. Okay, so it's beyond our comprehension right there. But okay, even so, what if you were to walk across the universe at a rate of 1 centimeter per century? Okay, 1 centimeter per century. Here, I just did it. Did you see that? I'll do it again. There's 1 centimeter per century. Okay, so if you walk across the whole universe that slowly, I calculated it, it takes somewhere around 10 to the 45th seconds to walk across the universe, somewhere in that order. Okay, so that's as big of a number as I could ever conceive of. 1 with 45 zeros behind it. If you were to take the ln of that, that's as big of a number as I could ever conceive. If you take the ln of it, you check it out on your calculator. I think it comes out to something like about 5. Okay, it's just minuscule. Okay, so in other words, here's what's happening. Here's this graph right here, 1 over x ln of x. If you go from 1 all the way out to 10 to the 45th, the area underneath this thing has only gotten up to about 5. It's only gotten up to about 5. However, we can kind of cavalierly and casually say, oh yeah, it only goes to 5, but what happens as you go farther and farther, it'll just keep getting bigger and bigger, and that area is going to go off to infinity. So it's almost like we're using words we can't even comprehend when we say, oh yeah, this is going to go off to infinity, but it goes so slowly that by the time you get here on the x-axis, the area has only gone to 5. And sure, the area is going to eventually get to 10, and eventually it's going to get to 100, eventually it's going to get to 1 billion, it's going to go off to infinity, but holy smokes, this is the fast stuff right here, and by the time you went 10 to the 45th, it only went to 5. So there you go. So you can go on from here and say, what is a function which, so by the way, so this one now belongs right here. See this? This one belongs right here. That one diverges. So can you think of a function now that falls between this one and this one? Okay, this one converges, this one diverges. Can you find one that falls between them? Okay, what about, I don't turn it off and think about it on your own, and then turn it back on and think, well, what about this one? What about that one? How would that one behave? Okay, and I think you'll find that this one belongs in here. It's there. So now, can you find one between here and here, for example? And again, a lot of stuff, fun stuff to play with here. But how about okay, I'm just leaving you things to toy with, okay? Something like that. So I'm not going to go any farther, except you can ponder that. So we're up to 38 minutes already with this, and there's still a lot of interesting problems to do. So I'll now have another video after this one in which we look at some more interesting problems. So this will be it for this one.